Welcome, good morning. And today is webinar number 31 from the Australasian chapter of the International Geosynthetic Society, today on April the 28th. I will just short introduction. So we are the Australasian chapter of the IGS, and the IGS is a global society. It consists of 44 chapters globally, and there are 4,000 members, including corporate, individual, and student members. So the Australasian chapter, we cover the interests of Australia, New Zealand, and the Pacific Islands. If you become a member of the ACigs, you also become a member of the IGS, and to find more information about the IGS in general, you can visit geosyntheticsociety.org. This is their newly developed website, and on this website there are lots of resources available. There's geosynthetic journals, lots of information how to join. You can join technical committees, so it's worth a look at the IGS official website. There you can at the top of the page there, or the QR code in the bottom right hand side. And also we have our own website ourselves, the ACigs, and this has specific information about our chapter. So it's got information about becoming a either student, individual, or company member. We've got recordings of all our past webinars and events. We've got a useful news section, and there's some handy resources as well. So again, you can visit our website at acigs.org, or use the QR code there on the screen. As I mentioned, we've got a resources section on the website, and there's a vast library of information available there. It's got all the 30 webinars to date. Today's will also be uploaded there within the next few days. So a very useful resource to have, and there's some great presentations. So if you haven't seen all of the presentations done to date, you've got access to those by visiting the resources section on our webpage. If you would like a certificate of attendance for today's webinar, if you would like to email info@acigs.org, let us know your name and which webinars you attended, and we can organise a certificate to be sent back. This is just a quick reminder of our upcoming inaugural GeoANZ Geosynthetics Conference. Just 40 days to go now until the start of the conference, so be sure to register as soon as possible if you intend to attend the conference. We've got a great lineup of speakers. We've got Boyd Ramsey, Tim Stark, David Williams, Jorge Zornberg, JP Giroud, Professor Craig Benson, Malik Bouaza, and John Cowland, just to name a few. You can find a lot more details on geoanzconference.com.au. We're running 3 masterclasses at the beginning of the conference. So yeah, lots of information available on the website, and be sure to register because there's just 40 days remaining. So thank you to our sponsors for today's webinar. It's sponsored by TRI Australasia. So our sponsors allow us to run these webinars, so thank you, TRI. And on to today's webinar. So the topic for today's webinar is geosynthetic performance testing and integration of results, and this is going to be presented by Eli Cuelho. And a quick introduction. Eli, he is a senior engineer, and he's the director of the Transport Research, Testing and Services Division at TRI Environmental in the States.
And so really appreciate the opportunity here to be able to present to you today on this important topic, because it's, I think a lot of times manufacturers say that their materials work well and they have a certain design aspects associated with those materials, and yet if we don't have the testing results, then it leaves you questioning. So with that, I just wanted to start out my presentation by showing you where I live. I live in Montana. This is northwest of the United States. If you've never had a chance to visit Montana, you should take that opportunity. I'm actually not there now. I'm actually in our southeast United States lab in South Carolina. But this is where I live, and it's just about an hour and a half north of Yellowstone Park. So those of you who have traveled to Yellowstone Park have been near where I live. So I missed that because I'm not there this week. All right, let's start in. So when you're designing pavements, there are several objectives that you're trying to meet when designing a roadway. I mean, the primary objective is to provide something that's smooth and durable for the traveling public. So in order to do that, you have to have the proper structural design. That means you have to have materials that are stiff and strong. You have to provide good drainage. You have to make sure that the materials that you're using are high quality and that the construction is also done well. Even if you have good materials, but the construction is poor, then the roadway just won't last as long as you'd hoped. Of course, there are other considerations when building roadways, like safety, providing the right amount of friction and drainage that the road is safe to drive on. And then the design, of course, one of the objectives as an engineer is to try to make it economical, using materials that aren't too expensive and trying to be efficient with how you use those materials. And then finally, we also are we need to be sure to be environmentally sensitive, not to pollute, not to create noise, and to be carbon sensitive as well. So this presentation is going to focus on the structural design. It's not going to consider the safety and the economics and other factors, but it's just going to focus mainly on structures because we're using geosynthetics to make these roadways stronger, and that's the aspect that I want to talk about today. So when it comes to structural design, the basic idea is you have a load that's applied to the surface, and that load is the greatest at that surface. The pressure is the greatest. And as the pressure distribution goes throughout the structure, it gets less and less in layers, as you see here in this illustration, where on the bottom, which it might be your subgrade layer, you want to be able to limit those stresses down on those lower layers because those tend to be the weakest. And the upper layers, like the asphalt layer or the base course layer, will be able to provide the structural support for the loading by limiting this straining and stressing out those lower layers that tend to be the weakest. So in geosynthetics, when you apply a geosynthetic, it's typically put in at the bottom of the base course layer. In this case, you're just seeing an unpaved roadway illustration here with the geosynthetic at that bottom layer. You can put the geosynthetic up into the layer closer to the load, and that does actually improve the performance some. But in this, I really wanted this illustration is meant to be able to show you that there are kind of two main ways that geosynthetics might be used in roads. One where you have a really soft subgrade, and another one where you have a firm subgrade. And the soft subgrade, you can expect deeper ruts from the load. The material itself is put into higher tension beneath the load here, and which being supported just directly beneath through this high tension and this greater rut that you see here in this illustration. Whereas if you have a firmer subgrade, typically those are the roadway is not going to be able to tolerate the rutting, and so it's maybe a more traveled path that can't tolerate the rutting. And in this case, the geosynthetic is now part of the design, and you'll see here that the stresses are limited, but they're being borne partly by the geosynthetic at the bottom of the layer. So for this, taking the first case where we have a subgrade that's on very soft ground, the soft ground may be just a low shear strength, maybe it's highly sensitive to water, but typically you're looking at CBR, California bearing ratios, that are between 1 and 3. I'm not sure if this property is used in Australia for design, but maybe if it is, then California bearing ratio is oftentimes used here for characterizing the strength of the subgrade. You can have a high water table, which creates some of this mess you see here in this photograph, or a high plasticity index. However you slice it, this is a bad situation that you don't want to run into. And in this case, you can use the geosynthetic to be able to create a platform where you're not just pushing all of the gravel layer down into this muddy mess below it. Where you have a firmer subgrade, now you are you're incorporating the geosynthetics not only as a means of just being able to pass over the structure during construction or throughout the life, but now it's for a longer period of time, and so it becomes part of the design. And you need to be it's a little bit more sophisticated, trying to be a little more efficient. And you can do it in one of two ways, where you use the geosynthetic to be able to limit. Maybe you want to reduce the section thickness, so you can rely on the strength of the geosynthetic to be able to provide some of that, some of the structural support, or you can actually use it to increase the length of the lifespan of the roadway. And this tends to be on roadways where you have a CBR of the subgrade maybe between 3 and 8. Anything above 8, there's minimal benefit from the geosynthetic, other than maybe using a textile or something like that for separating the layers from one another. But in terms of structural support, anything above an 8 is really not that beneficial. So now just talking a little bit more in detail about these mechanisms that we see throughout the pavement. Again, we have a road surface here with a tire on the top. And as the tire is putting pressure down, the stresses are being transmitted down through the base course layer. And eventually they intersect this geosynthetic layer, which in this illustration is at the bottom of the base course. And as it approaches that layer, you can see here that the stresses begin to bend, and they bend and turn to the side. And this is just part of the reason for that, is because the geosynthetic is providing lateral restraint to the gravel that are at the bottom of that layer. They're not allowing that gravel to spread out of the way. If the gravel is able to spread out of the way, then the tire will create a rut in the surface. And so you're trying to limit the rutting of the roadway. This also has the effect of widening the distribution angle. So as the distribution angle goes at a certain angle down through the structure, it begins to widen as it comes down here toward the bottom, where this lateral restraint is happening. And what that does is it increases the horizontal stresses in this area, but it reduces the vertical stresses. And what you see is then a jump in the stiffness based on the fact that the geosynthetic is in this structure. And beneath that, in the subgrade area, now you see a reduction also in the vertical stresses, but you also see a reduction in the shear. So you're not going to have as much deformation happening in that subgrade layer due to the fact that this geogrid or geotextile, whatever reinforcement you're using, is present in the structure. Now, there are many ways that you can measure the benefit of geosynthetics and roadways. There are 3 primary ways that they're calculated. I'm going to talk about each one of these. The first is traffic benefit ratio. It's also known as TBR. The second is a base course reduction factor, also known as BCR. And then there's also a layer coefficient ratio called LCR. And each one of these are commonly used in design. Probably mostly TBR and LCR. BCR and LCR are related to one another, and I'll show that here in a couple of slides. So in terms of traffic benefit ratio, TBR, you're basically comparing 2 systems that are identical to one another. The asphalt thickness is the same, the base course thickness is the same, and the subgrade is the same strength. The only difference between these 2 simulations is that one is stabilized with geosynthetic and the other one is not stabilized. So you run these simulations perhaps in the lab or on a full-scale test. And I'll go into methods of doing that. And you see that the geosynthetic is hopefully going to perform better than the unstabilized. And you make a comparison between the results. So this is some basic results that you might get where the unstabilized simulation reaches 25 millimeters of rut, say, in a short amount of time. And whereas the stabilized test section reached a much larger number of traffic passes than compared to the unstabilized test section. And so to calculate TBR, it's just simply the ratio at a particular rut depth. So let's just say your rut depth that you're interested in is 12.5 millimeters. At this rut depth, you just take the ratio of the amount of traffic passes that you got with the stabilized and dividing that by the unstabilized. And in this case, you get a TBR of 4, which means that the roadway that was that had geosynthetic in it was able to last 4 times as long in terms of the traffic benefit. And if you do this same analysis later on, let's say you are able to you're able to tolerate more rut, say 25 millimeters of rut. In this case, the TBR is actually greater. And so based on this calculation, you can use this in design to be able to anticipate how many traffic passes you might get from a stabilized versus an unstabilized road structure using geosynthetics. Base course reduction factor, or BCR, is a calculation made where you are comparing pavement systems with that lasted the same lifetime. They were able to accommodate the identical amount of traffic passes, but in this case, the geosynthetic reinforced test section was a bit thinner. The base course was just a little thinner than the one that was unreinforced. So this is a little hard to anticipate, and that's why most of the time the calculations are done using TBR, because it's hard to know exactly what this depth of base course is going to be without knowing how much benefit you're going to get from the geosynthetic. So there is an iterative process that you can use to determine this ratio. But if your design is to, say, save a certain amount of thickness on your road cross section, this might be the way to use it in your design, saying that I'm going to be able to reduce my base course by a certain percentage. And this is just another way of calculating the performance. And then finally, layer coefficient ratio is to determine the benefit, or try to quantify the benefit of the geosynthetic in terms of a modified thickness of the base course. So again, you're looking at it in terms of the base course thickness. And in this case, BCR is equal to, or LCR, excuse me, is equal to 1 divided by 1 minus the BCR in percent. So divided by 100. And so they're related to one another. And the way to get this LCR can be done theoretically by using the AASHTO equation. This is the American Association of State and Highway Transportation Officials equation that is commonly used as a simple way of designing roadways in the United States. And I'm not sure what equations are used there. If you guys are in a mechanistic design, or maybe someone can comment and let me know what that is. But there's a way to calculate that, and I'm going to talk a little bit about that now. Here's the AASHTO equation, and inside this equation, and I'm not going to go through all the parameters here, but the one that I want you to focus on is the structural number, which describes how strong the support is from the structural, the benefit of the layers. And the way that that's done is by having this equation, which is the structural number, where you have a coefficient that describes the structural strength of the particular layer. In this case, the A1 and D1 are for the asphalt, and D is the thickness. So you'd multiply those two together. And then base course has the A, again, it's a structural coefficient associated with the base course, multiplied times the thickness, and then also multiplied times the drainage coefficient. So this is how we calculate the structural number. And essentially what you're doing when you determine LCR is the LCR is a multiplier times the base course term in the structural number equation. So let's just say you had based on your performance testing, the test section worked much better. Let's just say it worked 20% better. You basically apply that 20% benefit to the base course term in this equation. So it would be a benefit in this case of 1.2 multiplied times that turns, which makes the base course seem like it's a little thicker, or it makes this A2 term seem like it's a little stronger. However you want to think about the LCR, it's basically to modify the second term in the structural number equation. So LCR obviously should be greater than 1 to be able to apply that increase in the structural number to the design equation. So that's basics about what kind of structural, or excuse me, the way that performance is calculated. But here's how I wanted to talk a little bit about how you get those performance information in the first place through different testing. And this is something that we do it here at TRI, and it's something that I've done for quite some time now. And so I wanted to at least share with you some ideas about performance testing, because As many times performance testing can be done poorly, and there are good ways to do it. So probably the biggest key to doing performance testing, either in the field or in a lab, is to make sure that there are consistency between the test sections. You're trying to compare the do nothing case to the one where the geosynthetic is in the test. So if everything is the same except for just the geosynthetic, then you have a good way to be able to compare those one to another. Without that, it's very difficult, and all the competing factors that are associated with roadways begin to outweigh some of the other elements that make it easy for you to calculate performance. So that is probably the key element to be making performance testing work well. Of course, you got to select good materials. You got to place those materials. If you're doing it in a lab situation, you want to make sure this is as realistic as possible, and making sure you're hitting all the proper tolerances and doing the QA, QC to ensure that the test sections are built similarly to one another. And there are different methods of doing performance testing, all the way from full-scale tests out on an actual roadway, to doing something maybe larger scale, but in a laboratory with accelerated pavement testing, or some sort of smaller simulation in a lab using a smaller box or something that applies a load. And to know which test method you might want to use, you're basically going to balance realism with cost and time and effort. The more realistic it is, probably the greater effort it is, and it's going to cost you more. So that there's some trade-offs, but the smaller simulations can tell you a lot, and they're maybe more rapid and just as well. So it depends on your budget and what you're after. So a full-scale test section could be on an actual road, like I said before, or it can be a controlled experiment. And it's the most realistic because it's done with full-scale equipment. It's oftentimes has the longest timeline because you're relying on actual construction and all that goes into that. But you tend to lose a little control, especially if it's on an actual roadway, because the contractor wants to do this as quickly as possible, and you might be a thorn in their side as you try to do this experiment in the midst of all their trying to make money. These tend to be higher cost, but again, if you do this just on an actual roadway, and you don't really care about all the details of making sure the test sections are similar to one another, then you can strip some cost off. But then when you go to make your comparisons, you're gonna suffer there. So there's always this balancing act that you have to do to try to figure out the right way to do it. And I'm going to give you an example of a full-scale research project that I led when I was part of Montana State University back in the mid 2000s. 2014 is when we completed the project. In this research project we had 17 test sections. I'll show you what that looked like here in a minute. And we wanted to look at the geosynthetic material properties themselves to see which one actually was related directly to performance in the field in this particular application. And this was a subgrade stabilization application, so it was a very soft subgrade, a CBR of approximately 1.7. And we wanted to understand those mechanisms by which the performance was enhanced. I'll talk a little bit about that. And then we calibrated the Giroux-Han design equation for a particular material property, which is the junction stiffness. And I'll show you how that was done as well. In this experiment, we had 17 test sections, as I mentioned. There were 3 test sections at the beginning where we had an integrally formed grid. It was the same grid in 3 of those test sections. Oh, excuse me. And each test section was 15 meters long and it was about 5 meters wide. And in these test sections, we had the same base thickness of approximately 27 or 28 centimeters all the way through. All these test sections had the same base thickness. But these first 3 test sections actually had a stronger subgrade on the end and a very weak subgrade here. And then all from 3 all the way to the very end had a subgrade strength of about 1.8%. So what we're trying to do here is we're trying to vary the subgrade strength to see what effect that has on the performance. And on the other side, where we had the controls where there was no geosynthetic, we actually increased the thickness of the base for control 2 and then even thicker for control 3. Like you can see the thicknesses of 41.4 and 63.2 centimeters. The nominal thickness was, again, approximately 28 centimeters. So in this way, we set the experiment up so that we could back calculate what the effect of gravel thickness was, as well as the subgrade strength. And then in the midst, of course, we have all these different materials that we were able to test to be able to see which material worked well and why it worked well. This is the trench that we dug on the test site. This is not on an actual roadway. It was on an old airfield that we were leasing at the time. This is mixing the subgrade and putting it in the trench. We had to mix it at the right proper moisture content to make sure that it was exactly the right strength the entire way. It's very wet. Like I said, a subgrade CBR of approximately 1.8%. Once we got the subgrade finished, you can see here in the background, we have this kind of this wall, and we had struck this off so it's all smooth and flat. And then we can see we're adding the instrumentation with the geosynthetic. Here is a picture that shows each one of the geosynthetics that we used, starting with an integrally formed grids. These are very common materials. Then there's a welded grid that we used, another welded grid. You can see the different types here, and you may be more familiar with the brand names of these. We also used 3 different woven grids. You can see them featured here. And then one knitted grid is a different style of grid. Another had a triple layer extruded grid. And then 2 other integrally formed grids here, the triangular shaped apertures. And then finally, we used a woven textile and a non-woven textile for each of the test sections. So these are the different materials that we used. Finally, we went to put the materials in, we covered it with base course and drew some lines on there so that the truck driver could stay in the right spot with all the instrumentation. And then we drove a truck over it. It was a fully loaded 3-axle dump truck, drove across at approximately 10 kilometers per hour. And this is the response we got. And I'll just go through this really briefly. I want to just point out a few things here just to show you how some of the test sections performed. The ones, the stars here on the left, that's control 1. That had the thinnest base course, no geosynthetic, so it failed quickly. You can see it was less than 100 truck passes before it failed. And then on the other end, you see the one with the X's here on the bottom, that's control 3. It had the thickest base course. So between these two, you can see that most of the test sections fell, of course. And control 2 is here. This had the thicker base course than the nominal test sections. So it actually performed better than all the reinforced test sections. And you can see that this one here with the diamond, for example, is the woven textile. Over here with the X, you have a knitted grid. So all of these in between obviously did better than doing nothing, but didn't do quite as well as thickening the base course in these 2 ways that we did here. So we took that information and we calculated the TBR. This is traffic benefit ratio at a particular depth of rut. In this case, it was 63.5 millimeters of rut. We did the analysis, and we also calculated the amount of base course reduction. So what I want to show here, at least primarily first, is that all these values of TBR are positive, meaning that every single material was able to improve the performance of the test section when compared to the control. And even the worst performer, this is the knitted grid, had a base course reduction factor of almost 10%. So you can reduce the thickness of the base by 10% in this case. The best performer was the woven geotextile, and it had a traffic benefit ratio of almost 15. So meaning it could accommodate 15 times more truck traffic than the control. And the base course reduction was somewhere around 27%. So you can just see the range of the different products here and how they performed in the field. We also put in some instrumentation. We wanted to measure what was going on. This is the behavior now side of it. So we had strain gauges and LVDTs that were set in the ground to be able to look at movements. And this is sort of an illustration. The basic thing I want you to get out of this, not to get too stuck in the weeds here, but I just want to say that there's a transition from that lateral confinement where you see that the geosynthetic is providing some sort of resistance in the movement of the gravel in the lateral direction or horizontal direction. But eventually, once the rut gets too deep, then you transition into this tension membrane where the material is just under a lot of stress and a lot of tension at that point. So there are different material properties that are sort of associated with those two ends. Like the first part where you have the tension, you're going to be relying on something different than if you're just relying on pure tension when it comes to the higher deformations. And I just want to show just maybe an illustration of kind of how this might look if you're seeing the truck going through the test sections. You see these two little red arrows down here that as the truck continues to go past, the red arrows and the stresses in the material begin to accumulate. Okay, they're not going to, once the rut forms, it's always going to have that stress on the geosynthetic. So you can see that the stresses get highest after many truck passes. And I'll just show this in the plan view as well, because I think it helps to illustrate this. So you see as you go across, you're pushing outward from the different tires on either side. It's forcing the gravel in that direction, which is the stresses are then increasing in time as the traffic is increased across the test section. So eventually you have high stresses that are outside each of the wheel paths in this direction. And if we take a piece of geogrid, in this case a biaxial geogrid, we can see that as we have those stresses are being borne by these cross members that are in that direction. And then the tension is being borne by the straps that are in the direction transverse to the driving. So the truck is going across side to side on this slide, and the stresses are being applied in the opposite direction. And there's actually a test at ASTM that looks at that particular property. But we had lots of different properties of the material we looked at. Here we looked at the wide width tensile strengths. We looked at cyclic tensile strengths. We looked at the like a pull-out test where you look at the resilient, the interaction between the geosynthetic and the gravel. And we also looked at this test where it's called junction strength. We also looked at aperture stability modulus, which is in the G-Rohan equation. And what I'm showing here on this slide is that the R squared, which is how well a linear regression fit between the materials that were used, that had varying, these properties were different between the different materials, and how well that fit the performance data. And what we see here is that the R squared is highest on the junction strength or the junction stiffness, how well those junctions and that material are set with one another, how strong that is. And that makes some sense based on what I showed you earlier and how the stresses are born in the material. So this is that test. It's an ASTM test. And basically you pull down on this cruciform shaped material, and that junction is stressed by trying to shear one versus the other. And that we found that property, again, really matched well with performance. And in this case, the stiffness is just the initial part of the curve. So that's how we calculated the stiffness of that junction. And we wanted to say, okay, now the G-Rohan equation, which is this hairy, big equation. If you haven't seen it, I don't mean to intimidate you, but or I'm not going to go through it in detail by any means. But what I wanted to point out is that this K factor is really what describes the geosynthetic component in this design. And the J here is the aperture stability modulus, which is a test that twists the junctions of the geogrid. We didn't find that was related to performance. In our case, we found this junction stiffness was related to the performance. So we basically modeled that and through a series of mathematical work, we essentially modified this K term in the G-Rohan equation to be able to accept this property rather than using the original one of aperture stability modulus. And this just shows an illustration of how you might do that. You calculate this junction stiffness, you come up here to the amount of rut that you might be allowed, and you get this K prime factor from this chart, and then you can use that in the equation to solve for the thickness of the gravel. All right, and so you might be wondering, well, the textile was the one that worked the well, so worked the best in our test section. So what happened there? It doesn't have these little junctions, but I think that in textiles, how they're woven, all those little junctions are in touch with one another after they're being confined by the gravel, and they are allowing that stress to be transferred. And because it's a full membrane of material, it allows those stresses to be transferred in basically an infinite number of intersections. So I think the idea is that it's just a lot of stress paths, and those stress paths are shortened when it comes to a textile because it's continuous, whereas the grid has a lot of open space there where the rock can be able to get in touch with these members, and the members are able to bend and that kind of thing. So I think that there's some thoughts about that, but we didn't have enough textiles in our test sections to really show exactly what happened. So that was just based on our intuition. And so for this subgrade stabilization application, we allow for very large ruts. There's an early reliance on to resist that lateral movement, as I was saying before, and I think that is related to this junction stiffness property. But later on, as those ruts develop, there's a greater reliance on the tensile strength in the material itself, and we saw that through our mathematics. So that just shows you what was done in a large scale test. Now we're going to move on to something that's more laboratory derived. Here it just shows a video of our test device in one of our labs where we built a paved simulation. In this case, it has approximately 75 millimeters of asphalt on top of 300 millimeters of base on top of a subgrade CBR subgrade of approximately 2. So these are very realistic test sections. You can build them with full scale equipment. You have a lot of tighter construction control because it's smaller, and you can control that timeline, and the costs become more reasonable when compared to the tests I just told you about. And this can be broken up into individual test sections to look at various different parts of your design. This is the test pit. Test pit is, well, I put this in feet, and so you'll have to convert, but 11 feet, I think it's 3 or 4 meters by approximately 11 meters long and about a meter, 1.2 meters deep. And so this just shows a concrete lined pit where we can build these test sections. This is us installing the subgrade. We mix the subgrade up to a certain moisture content, compact it in place with machines and a roller here, just showing us later on in our construction. And then we level the subgrade surface off to make it smooth and all the same depth. And this just shows the finished subgrade surface in this case. And we do lots of tests on it to make sure that we are getting the same properties. We're doing all the properties to make sure that each test section is built identical to one another. And this just shows what it looks like with in this case, there was a couple of geotextiles that were used to reinforce the test section. In the foreground, you see the control that did not have a geosynthetic in it. This shows the base course being installed. And then finally, we paved. You see it's all done inside of a building. The building is climate controlled so that when we're testing, everything's kept the same. And then this is, again, just showing our test device here that is being able to roll over and provide the traffic. And you get results that, like I was showing before, there's something like this. These are actual results of a test that we did for a client. You see the control over here has not had as much, did not perform nearly as well as the reinforced test section in this case. You can calculate TBR, you can calculate LCR using this information. Another test, now this is smaller yet, this is a box, it's approximately 2 meters wide by 2 meters long and approximately 2 meters tall. So it's probably the least realistic partly because it's a plate load test. Here you're just applying a load to a plate that's stationary rather than having that rolling wheel load that's a little bit different. But you get a high control because it's such a smaller amount of volume, so you don't have to build as big of a simulation. It tends to cost a lot less. And you can do individual test sections. Each one is tested, and then you start completely over with a new test section when you want to make the comparison. And this just shows us building a subgrade in the box using a jumping jack compactor. With the geosynthetic in, we can sometimes run here. In this case, you can see there's instrumentation being used to look at movements within the test section. Installing the base course with aggregate. And you can see here now we have to use a smaller piece of equipment. So we thin the layers down some to be able to make sure we get compaction. And then this is compacting the asphalt. And this is what it looks like when it's under the load. The load is the same. It's a fully, like simulating a fully loaded truck. It says 40 kilonewtons, and if the plate size is 300 millimeter plate. This is what it might look like afterwards. So to quantify performance, we looked at full-scale tests in the outside, maybe on a real roadway or in this, like we did, where we had a controlled area, a rolling wheel load test, a cyclic plate load test, which is a smaller box test that we showed you finally. And when you use those tests, you can calculate the TBR or the BCR or the LCR to whatever property that you're interested in, so you can use that in your design. Or you can interpret that design. You can interpret that information to be able to use it right in an unpaved or a paved road design, like I illustrated. And PRI does all of these things. And now that I've ended my presentation, I just had a couple of slides I wanted to introduce as we close out. TRI is also wanting to do a short course in Australia. It's possibly going to be a webinar, but it's to go deeper on this same subject and look at the fundamentals of road design using geosynthetics. In this design course, we would talk about the different materials that are used in structural design for roadways, common types, how they function, the mechanisms in the road, going into deeper into this analysis and deeper into the design of this particular topic, how pavements work, unpaved and road design, paved road design, talking about the AASHTO 93 method. All these different topics are going to be covered in this 1 day short course. The idea is here are the primary learning objectives: to understand the general structural behavior of unpaved and paved roads, to identify various geosynthetics and their associated functions within this application. Third, to design geosynthetic reinforced unpaved and paved roads, to become familiar with material properties and performance testing and of geosynthetics, to have an appreciation for related geosynthetic specifications and construction considerations, and to evaluate understanding through quizzes and practical design examples. Those are the objectives of this course that we want to put on. I think Warren and I have talked about when to do that, and we are shooting for later in this year, maybe in the October or November timeframe. So I'd like to maybe if it's possible to poll the audience to see whether they might be interested in something like this. With that, I conclude my presentation. I think we have some time for some comments or questions on what was presented.
Thank you very much. Yeah, very interesting presentation. It's nice to see all these different methodologies that are used to test the materials and how you do those. So got a question regarding the compaction. So what test do you undertake on the subgrade and base course to ensure that proper compaction's been applied? Yeah, so on the subgrade, we're not looking for a density, we're looking for a strength, and typically that strength that we're shooting for is a CBR. And so we'll have a target for that CBR strength, and we've done laboratory tests to relate CBR to an infield shear strength using a handheld vane shear. So for the subgrade, it's soft, and so we have this little, I don't know if you're familiar with the handheld vane shear, but you push it into the ground, it's got a little vane on the bottom of it, and you twist it and you get an immediate measure of shear strength. Now, the reason we use that is because it's pretty accurate, and it allows us to make sure that the test sections are done equally to one another. And we already have a relationship between the vane shear and CBR from a lot of different testing that we've done. So for the subgrade, that's how we generally do it. And then for the base course, we will take a density measurement using a sand cone. We also use a DCP, a dynamic cone penetrometer, to look at the strength that way. And then we also use an LWD. This is a lightweight deflectometer that puts the dynamic pulse down on the plate and gives you a direct measurement of the dynamic stiffness of the material. So we're evaluating it in a lot of different ways, and then all those test results will go into a matrix that tells us exactly what the test section
how closely they are related to one another in terms of their strengths. Their thicknesses are all the same, and we have very tight tolerances to make sure that the only difference between the test sections is the geosynthetic in this case.
Yeah, right.
Yeah.
Cool.
And we take moisture contents also. We take a lot of different measurements, but the primary one that we do for the subgrade is the vane shear. And I think we take on our rolling wheel load test, we probably take close to maybe 500 tests for a series of 4 different test sections. So there's a lot of testing that goes in to make sure that everything is the same.
Yeah, that's great. I think that's clearly answered that question. We've got another one here. In the structural analysis, there was drainage. How do you quantify the benefit of geosynthetics in terms of drainage in the pavement? Is it possible to quantify the drainage benefit of geosynthetics if the soil is saturated?
Yes, it is. Yeah, the geosynthetics that we use for our testing were primarily structural in nature, so there wasn't a drainage component, but there are some geosynthetics that do have either wicking capacity or you can have a drainage layer or something like that. And yes, those tests would be evaluated to see how they benefit the drainage, and then that would actually modify that M term in that equation. We didn't take that into consideration. We considered M1 for the sake of our analysis, because those geosynthetics just simply were not meant to improve the drainage whatsoever. Textiles and grids typically don't do that.
We've got another one that's just come through. So what is the feasibility of use of geosynthetics based on the BCRs recorded during the testing? Reductions of 10 to 20% in base cost depth would be in the order of $15 per square meter of roadway. How does this compare with the cost of supply and placement of, say, a woven geotextile?
Yeah, that's a good question. I don't know the costs of these materials, but I think that at about, this is kind of a guess, and it's mainly based on my intuition, that I would think that right around 25 to 30% savings in base course will break even with the textile in terms of structural strength. But if you think about, like for the textile, for example, you're getting also a benefit in separation, which is going to lead to a longer lasting roadway, because it's not going to allow those materials to mix, especially if it's saturated. So it's a really good question, but I just don't have enough information on the cost, because those costs are, I think the manufacturers would probably know that better than I would. Sorry to have to punt on that one, but I just don't know the costs. You change too much.
Okay, we'll be able to.
I will say that the non-woven textiles, for example, are relatively inexpensive, and they should just always be used, especially in soft subgrade situations, because they'll separate those layers from one another, and the benefit is very good, even if it doesn't create a base course reduction. We found that in our situation, even a non-woven geotextile will actually structurally benefit the roadway. And so beyond being a separator, it also provided structural benefit as well.
I've got one more here. So comparing the Giraud hand method with aperture stability and the junction stiffness, what difference in the gravel thickness did you get from these two equations?
Oh, that's a good question. Boy, that is a really good question. I think I did do that analysis, but I don't know the numbers off of the top of my head. I am so sorry. That's a really good question, though, because they do use the different material properties. We just found that, I think the biggest thing for us was that the material property of aperture stability modules just didn't seem to relate to the performance. But if it has a stiffer aperture, it may relate to a stiffer junction stiffness also. So, and maybe perhaps those two material properties are related to one another, and you get a similar amount. But that's a really good question. I'm sorry, I don't have enough information on that right now.
All right. In terms of the three methods that you you presented on in terms of testing and performance testing. I think there are at least for the cyclic plate load testing, there's an actual standard in development for that, isn't there?
That's right.
What
yeah,
about
I'm currently putting together the standard for the cyclic plate load test through ASTM right now. It's being balloted. Yeah. I'm sorry I interrupted you.
It's okay. I was just going to say, what about the other two methods? Are there some guidance in terms of how those, some standardized guidance in terms of how those test setups are placed? You know, there's like this guidance for installation damage, for example. Is there similar sort of guidance on those other performance tests as well?
On the other performance tests, such as the rolling wheel load, you mean?
Yeah.
Yeah, there's no guidance currently on those. And I'm going to work on that once I get the cyclic plate load test standard completed. But the idea behind the standard is to help make sure that the test sections that are being compared to one another are identical. And so there's a series of measurements that you should make and how much tolerance of difference you can actually tolerate, because they're going to be different by a certain amount. You just can't make them precisely the same, but you do the best you can. So, you know, thicknesses, making sure the thicknesses are the same and the strengths are all the same, the water contents are all the same, the densities are all the same. All that has to be done similarly between test sections if you're going to make a direct comparison between them. And that's mainly what those test methods are to do, as well as outline the load pull shape, what else do we talk about in there? You know, your how you make the measurements, how you the instrumentation that you need, the sizes of the plates, and all that has to be, you know, documented for the cyclic plate load test. But the rolling wheel test is a little more difficult because everybody has a different style rolling wheel tester. And I think that when I put that together through STM, it's going to be more of a guide rather than a test method. Yeah. That's my thought on that.
We've got 5 more minutes, 1 more questions come through. So if you don't mind, we'll maybe address it.
Yeah, sure. That's just fine.
The Druid hand method was initially developed with aperture stability index for biaxial grid. How could that be extended for multi-axial type geogrids?
Yeah, that's a good question also. We did have a couple of multi-axial materials in our test that we did. And you are able to get the junction stiffness from those types of materials, even though they have these unusually shaped apertures. And I know that there's. Sorry.
Is it just a different type of gripping mechanism to hold the?
It is a different type of gripping mechanism. That's right. Yeah, and there's a full report that was done, and it's on the internet, and you can download that for free. That gives you a lot more detail on what was done during those tests. And I show the photograph of how it was clamped and all that for the triaxial materials. But there is a new multi-axial materials, and there's all kinds of different shapes now. And it does become more difficult to try to tease that property out when the junctions and the material shapes become too complicated. The idea, though, is that the stresses have to be borne by those cross members and into something that's going to be strong in the transverse direction. That's the side-to-side direction of the roadway. That is the key there, that you have to be able to somehow transmit those stresses in that direction to make the roadway last longer. That's the basic principle behind that junction stiffness.
Okay. All right. Well, we don't have any more questions, so. Thank you very much, and as it's getting probably quite late with you there, I think we should let you rest now. And thank you very much. So
yeah, you're certainly welcome.
Providing an interesting presentation for us. Sorry.
Well, I was going to ask you, Ryan, if there's anybody in the chat that has, or the questions that have responded to our query in terms of whether or not they would be interested in a half day or full day. More in depth on this particular topic of trying to design for roadways, where you get into design examples and get into some of these, like the costs and whatnot, to be able to do a full design. is that something that's of interest to the folks that have participated today or not? Does anybody comment on that?
We've had a couple of responses saying yes, there is some interest in the course. So I'll give you some details afterwards of
Okay.
the responses. So yeah. Sure.
That's good. And then of course Warren from TRI Australasia is there, and you can certainly let him know whether or not you're interested in something like that. And he and I are working together to put that together. So really appreciate the opportunity today. It's been good.
No problem. We just had there was another question. It was just asking if it was possible to have the slides as a PDF. I mean, the presentation will be available on the ACigs website, but if the PDF of these slides is available, we can pass that on as well. If that's
no, okay. I think we can make that available. Yeah, for sure.
Yeah. All right. Thank you very much. Okay.
Okay, Ryan.
Thank you very much, Eli. And just to conclude, I was just going to say that there's no ACigs webinar for next month in May, as we'll be preparing to get ready for the GeoANZ conference. So the next webinar will be in either July or August. So look out for the weekly bulletins for who will be presenting and how to register on that. And otherwise, hope everyone has a great day, and hopefully see you at the GeoANZ conference. Thank you, everybody.
All right.
Cheers.
Thanks so much, everybody. Appreciate it.